Hello everyone, my name is K. Ranjit Kumar. Today I will be presenting my seminar on probability theory and stochastic processes, focusing on two key topics: power density spectrum (PDS) and cross power density spectrum (cpds). I will explain along with the properties. Before getting into the main topic, let me briefly explain what probability theory and stochastic processes mean. Probability theory is a branch of mathematical that deals with the analysis of random experiments. It helps us predict the childhood likelihood of outcomes in uncertain situations. A stochastic process is a collection of random variables that describes how a system evolves over time under the influence of randomness. In electronics and communication, we often deal with signals that vary randomly. For example, noise in communication channels. To analyze such random signals, we use power spectral density or power density spectrum. Power density spectrum (PDS). The power density spectrum or PDS represents how the power of a signal or random process is distributed over different frequencies. The power spectral density (PSD) of a WSS random process x of t is defined as the Fourier transform of its autocorrelation function Rxx of tau. It is given by Sxf omega is equals to integral minus infinity to infinity Rxx of tau into e power minus j omega tau into d tau. In simple terms, it tells us which frequency components carry the most power in a signal. And the inverse relationship is also true. The autocorrelation function can be obtained from the power spectral density using the inverse Fourier transform, and it is given by Rxx of tau is equals to 1 by 2 pi into integral minus infinity to infinity Sxx of omega into e power j omega tau d omega. Thus, the power spectral density and the autocorrelation function are Fourier transform pairs. We have discussed before the slide that concept is very important in fields like signal processing, communication system, and control engineering because it helps us understand and manage noise and other randomness effects in systems. Coming here, if x of t is a real process, then both Rxx of tau and Sx of omega are real and even functions. That means Rxx of tau is equals to Rxx of minus tau, and if Sxx of omega is equals to Sxx of minus omega. The alternative form of power density spectral is Sxx of omega is equals to limit t tends to infinity e of x of tau of omega square by tt. Here, st of omega is the Fourier transform of the truncated random process x of t over the interval minus t to t. Properties of power density spectrum. The power density spectrum has several mathematical properties that make it easier to analyze. The first property of PDS is the axis of omega is always greater than or equal to 0. The proof of this property from the definition, the expected value of a non-negative function, expectation of x of t omega whole square is always non-negative. Hence, Sx of omega is always greater than or equal to 0, so it is a non-negative value. The second property of PDS is the power density spectrum is always real and non-negative. The power spectral density at zero frequency is equal to the area under the curve of the autocorrelation Rxx of tau. That is, Sx of 0 is equals to integral minus infinity to infinity Rxx of tau into d tau. Here, the proof from the definition, we know that sxx of omega is equals to integral minus infinity to infinity rxx of tau into e power minus j omega t tau into d tau. If we place the 0 in place of omega, then sx of 0 is equals to integral minus infinity to infinity rxx of tau into d tau. Since it represents power which can never be negative, this property makes sense. No matter how complex a signal may be, its PDS will always show positive power values across frequencies. The third property of PDS is the power density spectrum of a real valued random process is even or symmetric about the frequency axis. The imaginary part of xxy of omega and the imaginary part of xy of omega are odd functions of omega. The proof of third property is consider xy of omega is equals to integral minus infinity to infinity rxy of tau into e power minus j omega tau into d tau. We can place cos omega tau minus j sin omega tau in place of e power minus j omega tau, and then here the cos omega tau will be 0, and then the sin omega tau will be remain here. At last, it will come as minus integral minus infinity to infinity rxy of tau into sin omega tau d tau. The physical interpretation is that positive and negative frequency components carry the same amount of power. The symmetry helps simplify analysis and calculations. Now, the IM of xy of minus omega is equals to minus integral minus infinity to infinity rxy of tau sin minus omega t d tau. Then it will be become my integral minus infinity to infinity rxy of tau into minus sin omega tau d tau, and it will be become as minus infinity to infinity rxy of tau rxy of tau into sin omega tau d tau. Hence, Im of xy of minus omega is equals to minus Im of xy of omega. Im of xy of omega is an odd function of omega, and similarly, Im of xy of omega is also an odd function. The fourth property of PDS is the power density spectrum is the Fourier transform of the autocorrelation function of the signal. Sx of omega is always a real function. The proof of fourth property is xx of omega is equals to limit t tends to infinity expectation of xt of omega whole square by 2t. Since the function of since the function x tau of omega whole square is a real function, xx of omega is always real. Now let we discuss about cross power density spectrum. The definition of cross power density spectrum is we have to consider two real random processes x of t and y of t. If x of t and y of t are jointly wide sense stationary random processes, then the cross power density spectrum is defined as the Fourier transform of the cross correlation function of x of t and y of t. It shows the how the power of the signal relates to another signal across different frequencies. It expressed as xy of omega is equals to integral minus infinity to infinity rxy of tau into e power minus j omega tau into d tau, and xy of x of omega is equals to integral minus infinity to infinity ryx of tau into e power minus j omega tau into d tau. By inverse Fourier transform, we can obtain the cross correlation functions Rxy of tau is equals to 1 by 2 pi integral minus infinity to infinity xy of omega into e power j omega tau into d omega, and Ryx of tau is equals to 1 by 2 pi integral minus infinity to infinity syx of omega into e power j omega tau d omega. Therefore, The cross PSD and cross correlation functions are Fourier transform pairs. This concept is very useful in systems where one signal influences another, such as in input output relationships, or filters, or communication channels. The second definition of cpds: if x of t of omega and yt of omega are the Fourier transforms of x of t and y of t respectively in the interval of minus t to t, then the cross power density spectrum is defined as xy of omega is equals to limit t tends to infinity expectation of xt star of omega yt of omega by 2t, and xy of omega is equals to limit t tends to infinity expectation of yt star of omega into xt of omega by 2t. The properties of cross power density spectrum. The first property of cpds is xy of omega is equals to xy of minus omega is equals to. The first property proof is consider the cross correlation function rxy of tau. The cross power density spectrum is given by xy of omega is equals to integral minus infinity to infinity rxy of tau into e power minus j omega tau d tau. Let tau is equals to minus tau. Then xy of omega is equals to integral minus infinity to infinity rxy of minus tau into e power j omega tau d tau. Since rxy of minus tau is equals to ryx of tau, xy of omega is equals to integral minus infinity to infinity ryx of tau into e power minus j into minus omega into tau d tau. Since xy of omega is equals to xy of minus omega is equals to xy of star omega. The second property of cpds is the real part of xy of omega and the real part of xyx of omega are even functions of omega. That is, real part of xy of omega and real part of xyx of omega are even functions. The proof of second property is consider xy of omega is equals to integral minus infinity to infinity rxy of tau into e power minus j omega tau d tau. Since we know here we can write e power minus j omega tau as cos omega tau minus j sin omega tau. Real part of xy of omega is equals to integral minus infinity to infinity rxy of tau into cos omega tau d tau. Since cos omega tau is an even function, that is cos omega tau is equals to cos of minus omega tau. Real part of xy of omega is equals to integral minus infinity to infinity rxy of tau into cos omega tau d tau is equals to my integral minus infinity to infinity rxy of tau into cos of minus omega tau d tau. We have replaced here cos of minus omega tau as in place of cos omega t. Real part of xy of omega is equals to real part of xy of minus omega. Hence, real part of xy of omega is an even function. Similarly, real part of xy of xyx of omega is also an even function. The third property of CPDS is the power density spectrum of a real process x of t is an even function. That is, xx of minus omega is equals to sxx of omega when x of t is real. Proof of third property is consider a WSS real process of x of t. Sxx of omega is equals to integral minus infinity to infinity rxx of tau into e power minus j omega tau d tau. Also, xxx of minus omega is equals to integral minus infinity to infinity rxx of tau into e power j omega tau d tau. We can replace tau as minus tau. Then s dash of xx of omega minus omega is equals to integral minus infinity to infinity rxx of minus tau into e power minus j omega tau d tau. Since x of t is real from the properties of autocorrelation, rxx of minus tau is equals to rxx of tau. Therefore, xxx of minus omega is equals to integral minus infinity to infinity rxx of tau into e power minus j omega tau d tau. Then xxx of minus omega is equals to sxx of omega. The fourth property of cpds is xy of omega is equals to 0 and xy of omega is equals to 0 if x of t and y of t are orthogonal. The proof of fourth property is from the properties of the cross correlation function, we know that the random processes x of t and y of t are said to be orthogonal if and only if the cross correlation function is 0. That is, rxy of tau is equals to ryx of tau is equals to 0. We know that xyx of omega is equals to s integral of minus infinity to infinity rxy of tau e power minus j omega tau d tau. Therefore, xyx of omega is equals to 0. Also, xyx of omega is equals to 0. That brings me to the end of my seminar. Thank you all for listening patiently. I hope this presentation helped you understand the concept of power density spectrum and cross power density spectrum more clearly.